welcome back to my YouTube channel. Now in this video, continuation from my previous video, I talk about frequency. I introduce about the wavefront of the crest and the trough. So this video, I'm going to talk about the relationship between the velocity, the frequency, and the wavelength. Now, I would like to stress again that you are supposed to have gone to your reference text about what is frequency and what is wave, right? So now, this part of the video, I'm going to demonstrate on their relationship, okay? Now, velocity here, as you have gone to, in wave is transfer of energy, the mass or the matter doesn't move. Now, I'm going to show you here. This one good example on the left here is how the wave move. This is not the ordinary ripple wave, but those line represents the wave. Okay, it's not the actual. It's a paper. I fold them into fan and open it up as an for illustration purpose. So I'll put in the side view. Say for example, this is the crest. So it would be like, okay, I want to do maybe the dark one, dark color. Okay, let it go up and then come down and then come up. So this is the crest, down, up, crest, down, and this is another crest. So continuing from our previous video, I mean equilibrium will be in the middle, right? In the middle somewhere here. Okay, it's not a straight line, sorry about that, I don't have a ruler with me. Then amplitude would be the distance from equilibrium up to maximum. So this is the amplitude. I think you have gone through that, okay? So, and wavelength is here to here, okay? And one wave in one to here. So now I'm not talking about that. Now, velocity, what does it mean by velocity here? Say for example, if it were to be water ripple, let's say this is a water. Let's say you drop one drop of water onto the surface of water. What happened? You get ripple. Okay, this is what you will see. Now, if I were to place a yellow duck, I will place a yellow duck initially. What happened? The yellow duck will, maybe this is the duck, will go up and down only. Okay, you don't expect this duck. It will go up and then come down. You don't expect the duck turns out to be here. Okay, the duck do not move from left to right. Only the wave, the crest, move up and down. Only the energy is transferred from left to right. The duck do not travel from left to right. Okay, I hope you really have gone through your reference. This is what it meant by a transfer of energy without the movement of any matter or object. By the end of it, the dart will remain here on the left. It just go up and down, but it doesn't travel from left to right. So what does it mean by velocity? The velocity means how long does it take for the molecule, the water molecule here, to go up. Because initially you expect it to be a calm water molecule. Only when a first droplet, then only you start to go up and down, up and down, up and down. So how long does it take for a crest here so that it will form a crest here? So this is what it meant by the velocity. How long does it take for this crest to occur over your right? It's not about the duck move from left to right. Alright? So make it clear, this is what it meant by the velocity. And their relationship to relate them would be V equals to F lambda. That's all. This is all you need to learn, and this is what you need to know. The essence is the mass or the matter does not move. It's just how long does it take for a molecule over the right appears, go up when you have some oscillation over the left. Okay, and as we have learned from 4, the unit is meter per second. The same goes with here to check left and right, make sure they are the same. So frequency it's 1 over second. This one is meter SI unit for wavelength, so therefore they are equivalent. Okay, then in some objective question that relates, instead of using equation, they put it into graph. So if in the event they want to relate f and lambda, so what happened is you put it into constant. F is direct proportional to 1 over lambda, right? So what happened if you were to have a graph of maybe f versus lambda alone only? What happened? It is inverse proportional. It's like this, inverse proportional, right? So another way to represent this curve, this graph, make it linear. How you do that? You invert it. What happened? Then it is direct proportional. F is direct proportional to the inverse of lambda, or F is proportional. F is inverse proportional to lambda. It's a matter of languages. Okay, so if you were to be the unit, most of the time the question tests you on this. If it gives you this one here, then the graph should be inverse proportional graph. If the unit turns out to be, the quantity here is 1 over lambda, then direct proportional. Alright, so what happened when some tricky question here is if you were given the speed of light, speed of light, how fast, in the first video I demonstrate that the light particle takes about 6.5 seconds to reach from the sun to the earth, because the light travel at this speed 3.0. You're supposed to, normally student doesn't need to memorize, but as time goes by, the more you use it, it will just get into your brain. The speed of light is 3 times 10 power 8. So what happened if you were given an axis, you want to plot, how about I have now the speed of light versus say lambda? What would it be? It's a constant number. Straight line. It's a constant. Per Mala constant, right? In vacuum, perhaps. Okay. So you may pause this video, pause it, give a pause. I think the first part is the interesting part. The dark doesn't go from left to right, but it just go up and down, right? Because it's a transfer of energy. Then you're advised to take at least 10 to 15 questions on this part. At least 2 to 3 publisher. Get those questions, because you don't have much, they test you on this V, F and lambda. Make sure the unit is consistent. Meter, the question gives you centimeter, and then the answer it asks you to choose might be in meter. So make sure first step will be to convert all the number with unit into SI unit. Okay, centimeter to meter, micrometer to meter, and then it's easier for you to get the answer, or depends on what the question asks. So now next, what happened next is some terminologies or definition in some objective question. Just before that, I missed out some important stuff. Here is, in real life, how are you going to see? Do you want to really witness it? Okay, this wave, because it's too fast, how are you going to see it? There's an instrument called Strobescope. Okay, I'm sure your school laboratory, I hope they would show you this, or maybe you should ask for it. You want to see the wave, they call stroboscope. Now stroboscope is comprises of actually a wheel with holes on it. Okay, with holes surrounding it, and it will of course rotate with a known frequency. I mean, this is a known frequency. You set it, a known frequency. You set this frequency, and all you need to do, you just point it, your eye, from your eye, look at it, look through it. Your wave, the wave you want to look at, some ripple you want to look at. You rotate it until you look through this window, this hole. The moment you see a constant flow, a constant wave like this, then the known frequency match with the incoming frequency. Or we call that natural frequency, perhaps. Then you will be able to calculate what's the frequency, where the frequency here will be equals to the wave frequency. Maybe we put it, the wave frequency will be equals to the number of hole times the known frequency. Okay, this is the known. You set it in your instrument. How many hertz? Look at it. Do you get a stationary wave? No. Then you increase the frequency until you get a stationary wave. Then you times the whole. Then you are able to tell what's the frequency of your wave. Okay, so that's the instrument that you use. Strobescope. Okay, you may rewind it to the previous minute. Listen again. What does it mean by stroboscope? Okay, next. Then maybe you have gone through it also. Some term called loudness. What does it mean by loudness? Very loud. What does it mean by loudness? Loudness has to do with amplitude, meaning high energy, right? High amplitude, high loudness. Another term called pitch. What's a pitch? Pitch has to do with frequency. You could have very low amplitude but very high pitch. You put in a graph, illustrate it better. It will be like the amplitude versus time, perhaps. Here, 0, very high amplitude, low frequency. For pitch, is that my frequency? What it mean? Same curve. What happened? Amplitude time. Over same time, you could have low frequency, but very, you can have very low amplitude but high frequency. Over the same time, you have many waves over the same time. Okay, so this is what it meant. And it's possible to tell another way to illustrate loudness and amplitude. Loudness is direct proportional to the square of amplitude. Just some objective question. Okay, just for you to know. Got to know this, then I think you're quite fit to go. Because next, another term they call resonance. In resonance, oops, my screen just come back to here. The resonance is what happened, as I shown in my previous example. I think I did show something like you have oscillation. What happened when you oscillate frequency? The one that you put into it is equivalent to its natural frequency. Don't memorize this. I will go show you an example by maybe external force. I mean, one good example from your textbook reference is a soldier when they pass through the bridge, hanging bridge, and not supposed to march, but they're going to they need to walk at their own pace, because otherwise you're going to have a huge oscillation and then the whole bridge collapse. Okay, we have a few examples in there. What does it mean by this is oscillation frequency, the one that you provide in some exercise or maybe in some reference? What happened is, if you were to provide a big, this is your speaker, okay, big speaker, okay, and then you have a glass, a wine glass perhaps, resting on, it's not floating but it is resting somewhere. So what happened in reality, if the frequency, this is called the oscillation, oscillating frequency. Oh, it's F already, yeah, okay. The one that you provide, if you increase this frequency until it is same as with the frequency of the glass, because in molecule, this is the natural frequency. When the frequency here, same as frequency here, what happens? You have resonance, and this thing will break. When it's here and in here, they are the same, then it will break. Okay, this is what you mean by resonance, because it oscillates so much until it breaks the mechanical force that bind the molecule in the glass. This is what happened. Okay, then it's all about it. Okay, oscillating frequency, the one that you provide, equivalent to its natural frequency. Natural frequency is the frequency where the atom vibrate in the glass, silicon, and they're the same. Then resonance effect will occur. Right. Then next term you have learned called damping from your reference text. Okay, you should go through it now. So what's damping? So damping is generally caused by resistance. Okay, you may refer to my first video. The object is bound by two springs, because I want to reduce something called damping. Here there are two springs so that it will oscillate over some time. Okay, what happened? Damping is not good for this case. There are cases where damping is good, of course. Resistance or friction. It's called resistance or friction. Or another way you want to put it, a physics way, you call the energy is being drained as heat. You have friction, you have resistance, you have heat. So you go through your reference. There are two types of damping. One is called external, and one is the internal. One way is look at it as in the spring. What happened? Internal damping. What happened? You have expansion or compression. Then you have internal damping. External damping would normally be a loss of energy as friction. Example. Okay. So there are two types of it. Now, one way to look at it is something in objective. Normally, they will ask is like this: a graph. This chapter, for chapter 1, you need to deal with quite a number of graphs. You really know good at it. Maybe this amplitude versus time. So what happened is one way to look at it. I mean, you should take some good time to really study it. Is that says you have some wave goes. What happened is this is just my guiding line. I mean, the amplitude dies off eventually. It's my guiding line. It's not the actual line. It's the graph should look like, okay, so first of all you have go up, come down, up, down. In Form 5 additional maths, you get to calculate, right, when the amplitude dies off. Go through my Form 5 additional maths chapter 1, you get to calculate things like this, right? So there's some characteristic that you should know. For damping, the frequency, they are going to be the same. Okay, so here to here, let's say the time is same t. I use another way of doing it. Say let's say I measure my time here to here is one wave. The time for each wave are supposed to be the same. Time are supposed to be the same because the frequency is the same. Okay, time is the same, frequency is the same. What changes would be its amplitude, and energy of the system. This one decrease. It reduces over time. Okay? Because here the amplitude here up to here is, let's say I have A0. This one here to here amplitude, not this one is A1. And eventually A2, A3. Where A0 bigger than A1, bigger than A2, bigger than A3, and so on. Okay? That's basically all about this part. Because in next part, I think you should pause my video and then go through the previous beat to see which part you have missed out, or go through your reference book, reference text. So the essence for damping, the time are supposed to be the same, time is the same, amplitude only reduces. This is what you need to capture in your mind for damping. That's why I have colors helps you to memorize, I hope. Okay, then before I stop for the next video, the final part that I want to summarize here would be the types of wave. It's also in your reference. Maybe you have gone through in the first part. Okay, there are actually two types of wave available. Okay, one is called I think I've gone through it because normally they were put in the first part. Transverse, because it's easier for you to understand now. Transverse, and another one is called longitudinal, because I don't think it's important you want to put it in the first, so I put it in the middle. Okay, longitudinal wave, transverse wave. One way is because look at transverse T. It's what happened. I have normally shown from first video. You have a sinusoidal wave like this. Okay, what happened? The object do not move, right? The matter do not move, correct or not? The object stay up and down. Let's say you have a duck here, it travel only up and down, but the wave travels from left to right. This is the direction of travel. This is the movement of the molecule. Movement of molecule or movement of a dark. Let's say you have a dark, a matter perhaps, or mass. Okay, you have a dark, lousy dark. Okay, we just move up and down, and the direction of wave is from left to right. So those are called transverse wave. Where if you want to put into a more physics way or scientific way, or the vibration, this is vibration, is perpendicular, because the vibration is perpendicular, meaning it's 90 degree. Yeah? 90 degree. Vibration is, I think you need to learn this word by now. Serenyang in BM we call it. Perpendicular. Perpendicular. Vibration is perpendicular to the direction of propagation of wave. Okay, so what are the examples? I hope you know it by now. First one would be called the water wave, the one that I shown. Water wave. In your school example, they will show you also water wave, up and down, and then the wave travel from left to right. Another way that you can't see it, but actually you face it every day, is called the light wave, or the electron spectrum wave, EM wave, radio wave. They are all considered as transverse wave that travel in vacuum from the sun to earth. Radio, X-ray, they are all transverse wave. And the only longitudinal wave, boys and girls, what will be? They're called sound wave. Sound wave is the only longitudinal wave, because what happened, you can't really see those, but unless you have the right tools. The air compress is like what I shown you in the paper, but it's not, the paper, but the line is the compress one side, and then decompress, and then they compress. 1, 2, 3, 4, and then so on and so forth. Okay, because here what happened, the vibration of the particle, left right particle, and it's travel from left to right. Okay, so what happened here is the vibration of the particle or the medium, a particle in the medium. In medium is a keyword because you need medium. Vibration of a particle in the medium is parallel. Okay, parallel is the word, or you call it along. Vibrate left, right, parallel, along the direction, along a direction of the wave. Propagate. Okay, so this is sound wave. Whenever you have sound wave, that will be longitudinal. The rest, transverse. Okay, that's basically all about it, because this chapter is about that. I think my last video for this chapter will be property of wave, where you get to deal with my next video. We will deal with what we have gone through, I mean, in Form 4, but this time now we're going to have reflection again. It's also the dualism of light, we will talk about it, reflection, then we're going to do it refraction, F-R-A-C. You have gone through Form 4, Chapter 5, I think you have these two terms you're quite familiar, but instead here you have a third one. The new one is called diffraction. It's the interesting one theory that we have. And then the last one we call superposition. You have a modulus Young experiment. Until then, kindly read through those reference, at least before reflection, diffraction. Maybe the way how the textbook reference arrange it might be different from my video. All you need to do is just go through it. It's not necessary that you must go through a book from 1, 2, 3, 4, 5. Sometimes you go to this part and then jump to another part, and then we'll come back to the part those we have gone through. Because the way that I arrange it, I suggest this is the way. I think I mean, from my experience, this is the way that you will memorize, you will understand this subject matter better. So that's why I arrange it this way. I think you will find that it's jumbled behind, and then some things come back. Okay, come back in the front. So that's all for this video. You may share my video through social network if it's good. I like those thumbs up. It inspires me a lot, and it costs you nothing. If you haven't already subscribed to my YouTube channel, subscribe to my YouTube channel for more upcoming video. Thank you.